Okay, hello. This is Chris Hanusa. I'm here to talk about U substitution. So U substitution is the opposite, the inverse operation to the chain rule. All right, what it'll let us do is it will let us take more interesting integrals. So if you remember, when we take the derivative of f of g of x, we get f primed of g of x times g primed of x. Right, so if we look at the simple example, if we take the derivative of the sine of 1 plus x squared, that's equal to the cosine of 1 plus x squared times the derivative of 1 plus x squared, which is cosine of 1 plus x squared times 2x. So if you look at the structure here, and we're going to be doing a lot of looking at the structure, then what we have is that here we have a composition of an outer function and an inner function. And this 2x here, this is the derivative of the inner function. Okay, so what that means is if we want to integrate a composition, so something like this, if we want to integrate a composition that looks like f primed of g of x, it better have the g primed of x hanging around. So what that means is if we wanted to go backwards here, we want to take the antiderivative of this, if we want to take the indefinite integral of 2x times cosine of 1 plus x squared dx, then we get sine of 1 plus x squared plus c. Right, when we go backwards, when we take the antiderivative of the cosine of 1 plus x squared times 2x, we're going to get the sine of 1 plus x squared, and over your constant. So what we're going to learn is we're going to learn about how to do integrals of this type and integrals that are not quite as obvious as this type. So let's talk about the strategy for how to solve this. And first we'll talk about, we'll write it out in words. So the substitution rule says if u is equal to g of x is a differentiable function whose range is an interval I, and f is continuous on I. So here's our setup. These are our hypotheses. Then if we want to take this integral of f primed of g of x times g primed of x, sorry, this is f of g of x. If we want to take the integral of f of g of x times g primed of x dx, then instead we can take the integral of f of u du. So what we're going to be ending up doing is replacing the g of x and this trailing g prime of x by a new variable u. And this is why it's sometimes called u substitution. So to do a u substitution, here are the steps you want to take. Number 1, search your integrand for a composition, something that looks like f of g of x. Next, we look at what the inner function is, and we say let g be equal, no, let u be equal to g of x. So we let u be the variable that represents the inner function. Number 3, we're going to calculate du, which is equal to g primed of x dx. So we have to take a derivative here. Number 4, do some algebra to replace all the x's and dx's by u's and du's. Okay, so if this is a definite integral, then replace also the bounds. So x equals a, we're going to figure out what u is equal to when x is equal to a, and we're going to have to figure out what if x is equal to b, we have to figure out what u is equal to in that case. We'll do some examples. The next thing we do, we have an integral in terms of u, so then integrate the new integral with respect to u. And number 6, if you have this definite integral, if it's a definite integral, calculate f of b star minus f of a star. If it's an indefinite integral, calculate, substitute back in x for u. I guess it's g of x for u. Okay, so we're going to do some examples. I suggest running through these examples. If you want to check on these steps, come back and replay it. Okay, so let's do some examples. Examples. So, examples. So let's find the integral of the square root of 2x plus 1 dx. So maybe can I bring this back in here? Let me see if I can bring this in here and give us the steps to keep in our mind as we're doing this. I'll put these steps back here, get those back in the camera angle. And why don't we also change the color of our pen? Okay, let's get a red pen, blue pen, and we'll hope we don't go out of focus here. All right, so we are supposed to, so in this integral, there's not very much choice. What's a composition? A composition, this is the square root of 2x plus 1. Composition is the square root of 2x plus 1, and the inner function here is 2x plus 1. So we let u be equal to this inner function. U be equal to 2x plus 1. Then du is equal to, take the derivative of 2x plus 1 with respect to x. We get 2 times dx. So that was the second step. And the third step. Now we want to replace in this integral all the x's and x's by u's and du's. So if we look at this, I'll replace x's, dx's by u's and du's. All right, so if we look at this, we get this integral becomes equals the integral of the square root of u. But now if we look at this, we have a dx here. So we'll rewrite this equation. Du equals 2dx by dx is equal to 1/2 du. So the 2x plus 1 becomes a u, and the dx becomes a 1/2 du. So that means what we have to do is we have to take the integral of 1/2 integral u to the 1/2 du. This is a simple integral that we know how to do. So 1/2 u to the 3/2 over 3/2 plus c. All right, let's simplify this a little bit. This is 1/3 u to the 3/2 plus c. Okay, we've integrated the new integral with respect to u. And this is an indefinite integral, so we have to substitute back in for x. Right? Our original function was a function of x, so the answer we need to get is a function of x. So the final answer is 1/3 times 2x plus 1 to the 3/2 plus c. Now, the nice thing about this process is that you can always check your answer. So you can always check your answer by taking the derivative. So if we want to do d dx of 1/3 times 2x plus 1 to the 3/2 plus c, what do we get? We get so 1/3 times 3/2, 2x plus 1 to the 1/2 times the derivative of the inside times 2. 1/3 times 3/2 times 2 is 1, and we get 2x plus 1 to the 1/2, which is what we started with. Yay! Okay, let's do another example. All right, example. Find the integral of x cubed times secant squared of x to the 4th plus 2 dx. All right, so now we look at this, and now it's a little bit more complicated. There are things hanging around that are not just compositions, but I do see a composition that makes me feel like, oh, maybe I need to look at it more carefully. I see the secant squared of x to the 4th plus 2. This is a composition with the inner function x to the 4th plus 2. So we let u be equal to x to the 4th plus 2. Then du is equal to 4x cubed dx. And now look at this. I see that we're kind of on the right track, because this x cubed dx, that's kind of hanging around here. We have this x cubed dx that's around here. So we're on the right track. And so let's replace the x's and the dx's by u's and du's. Okay, so what we're going to do is let's rewrite first. Let's get this du all by itself first. So what do we have? We have the integral. Let's put the secant squared of x to the 4th plus 2 by itself, and then see what we have left. We have an x cubed dx. Now, we want 4x cubed dx, so let's multiply and divide by 4. And the reason why we did that is because now we don't actually have to do any manipulations here for what the du is. We can just say, okay, well, we have a 4x cubed dx, and that's the du. So this integral becomes the integral of secant squared of u times du over 4. All right, let's factor out this 1/4. Integral of secant squared u du. Well, now this one we recognize as the derivative of the tangent. So we get 1/4 tangent of u plus c. And then don't forget to plug back in for what u is. So 1/4 tangent of x to the 4th plus 2 plus c. All right, and let's make sure that, remember, you can always go back and check to see that you have the right answer if you go in and do that derivative. Take the derivative of this. If you get to take the derivative, you should get the integrand that we had up here. All right, so now what I'd like to do is I'd like to do 2 examples of definite integrals. All right, example. Find the integral from 1 to 2 of dx over 3 minus 5x squared. Okay, so when I'm doing an integral and I'm going to have to use a u substitution, I think it's really important to keep track and put the actual variables on these bounds so we don't get lost. So I'm going to make sure to say this is the integral from x equals 1 to x equals 2 of dx over 3 minus 5x squared. Okay, so again, we're searching for a composition here. And what we see is we see a composition where the inside function here is the 3 minus 5x. So I see a 3 minus 5x squared. This is our composition. And the inside function is 3 minus 5x. So we let u equal 3 minus 5x. We say then what is du? du equals negative 5 times dx. Okay, so let's go back to what we said. So we calculated du. So if this is the definite integral, we're also going to have to replace the bounds. So if we have x equals 2, then u is equal to 3 minus 5 times 2. So we plug this x into here, and we got 3 minus 5 times 2, which is negative 7. And if x is equal to 1, then u is equal to 3 minus 5 times 1. 3 minus 5 is negative 2. So this is x equals 2. This is x. When x equals 2, u is equal to negative 7. When x equals 1, u is equal to negative 2. And that's important to keep track of. So our integral that used to be from x equals 1 to x equals 2, well, when x equals 1, u is equal to negative 2. When x equals 2, u is equal to negative 7. Now, these bounds are going from a higher number to a lower number, but that's okay. We need to keep the order that we had here, right? So when x was from a small number to a big number, actually that turns into u being from a big number to a small number, but that's okay. Okay, so we had our dx here, and we had a 1 over u squared here. So we're not quite done simplifying, because if you look at this, we have some u's, but we also have a dx. So we're going to have to simplify and say, okay, well, dx was equal to 1 over negative 5 times du. And so we get the integral from u is equal to negative 2 to u is equal to negative 7 of 1 over u squared times 1 over negative 5 du. Now this is an integral that's all in terms of u's and no x's, so we can take the integral. So First, let's factor out this -1/5. And then we have an integral from u equals -2 to u equals -7 of u to the -2 du. So when I take this integral, I get -1/5 times u to the -1 over -1 times, or evaluated from -2 to -7. Okay, so this is u is equal to 7, u is equal to -2. So now this is where I really like keeping track of what the variable is on the bounds is. If I had just kept 1 and 2 and I hadn't put the x's and I just kept going all the way through, we would be very tempted to plug in x equals 1 and x equals 2. But if you keep it around and it says x equals 1, x equals 2, and we're down here and we see x equals 1 and x equals 2, well, you would know you wouldn't be able to plug it in for the u. But now let's go ahead and plug it in for the u. First, the -1's cancel, and we're left with 1/5 times 1 over -7 minus 1 over -2. If you simplify that, what do we get? We get 1/14. Okay, so what did we do here? We did the same thing we did with the indefinite integrals. We figured out what the composition was, and we found the inner function, and the inner function we set equal to u. We set this inner function equal to u, we calculated du, and then we plugged in if x is equal to 1 or 2, that gives us that u is equal to -2 or -7. Fix those bounds, do the integral normally, and then we get the final answer. All right, I'm going to do one more example, and in this example, there's a little bit more algebra that's required. So sometimes when you're doing these, more algebra is required. So let's look at this one. We got the integral from x equals 1 to x equals 5 of x times the square root of 2x minus 1 dx. All right, so if you look at this integral, now you see a square root of 2x minus 1. Good. So that is the composition that we're looking for. So all this time you're going to be searching, and you're going to be searching for where is the composition. Well, we have to figure out where the composition is and then follow our nose. So we're going to let u be equal to 2x minus 1, and then du is equal to 2 dx. So that means that dx is equal to 1/2 du. We also are doing a definite integral, so we better change our bounds. So x equals 5 means that u is equal to 2 times 5 minus 1, which is 9. And when x is equal to 1, then u is equal to 2 times 1 minus 1, which is also 1. So let's set up our integral that we have so far. We have the integral from u is equal to 1 to u is equal to 9. We have an x, let's just leave it there for now, square root of u, and then dx is equal to 1/2 du. Okay, so if you look at this, we've got everything is good except we have an x still hanging out here. So what are we going to do with that? Well, we need to replace all the x's and dx's by u's and du's. So we have to find some way to replace the x by u's, and what we have is we have this equation here. So if u is equal to 2x minus 1, then that means that, so if u is equal to 2x minus 1, then that means that u plus 1 is equal to 2x, and that means that u plus 1 over 2 is equal to x. So this is a way for us to replace the x by something in terms of u's. So the next step here is the integral from u equals 1 to u equals 9 of u plus 1 over 2 times square root of u du. Okay, we should feel a little bit happier because we have an integral that's all in terms of u. We have no more x's around, so we should feel a little bit more comfortable with this. But at the same time, we still, like, this is a product, and we don't have any rules for how to take an integral over product. That's what we'll learn in integration by parts later on, but that's next semester. But we can actually do this. When you see this as a polynomial and this is some roots, we can expand everything out. So first I'm going to take out the 1/2. U equals 1 to u equals 9. And then we have a u plus 1 times u to the 1/2 du. And with this, I'm going to distribute it. I'm going to say, take 1/2 and distribute the u plus 1 times u to the 1/2, integral from u equals 1 to u equals 9 of u to the 3/2 plus u to the 1/2 du. And we integrate this, so 1/2 u to the 5/2 over 5/2 plus u to the 3/2 over 3/2, evaluated from u equals 1 to u equals 9. Okay, let's simplify this again. So we're going to bring in the, we're going to split it apart. We have 1/5 u to the 5/2 from u equals 1 to 9 plus 1/3 u to the 3/2 u equals 1 to 9. So remember, this is when you have a 1 over 5/2, that's 2/5. 2/5 times 1/2 is 1/5. 1 over 3/2 is 2/3. 2/3 times 1/2 is 1/3. So now we can plug in the values. 1/5 times 9 to the 5/2 minus 1 to the 5/2 plus 1/3 times 9 to the 3/2 minus 1 to the 3/2. 9 is 3 squared, so this actually ends up being 3 to the 5th minus 1. And then the square root of 9 is 3 to the 3 is 27 minus 1. And so you keep this up, we get 1/5 times 242 plus 1/3 times 26. And the answer is 31.866666. All right, so what did we have to do here? What we had to do here was we had to do a little bit more of the manipulation to figure out how to replace all the x's and dx's by u's and du's, and the rest is taking a normal derivative, a normal integral, like we have been. All right, so there are some examples. There's an introduction to the u substitution. There are some examples. Now it's time to practice. Now it's your turn. So remember, you can always go back, replay some of these videos, some part of this video if you wanted a recap, and I will see everybody soon. Bye.